It has been 2 years since NASA's James Webb Telescope gave us a stunning first look at the depths of our universe.
The revelation that the James Webb Space Telescope JWS has finally pulled back the curtain on a hidden facet of Pluto is nothing short of a paradigm-shifting moment in planetary science. For decades, Pluto was viewed as a remote, frozen world on the fringe of our solar system, studied briefly during the New Horizons flyby in 2015, and long assumed to be relatively inert compared to the great planets. But JWS's latest observations have forced a radical rethinking. What we thought we knew about Pluto, and by extension the distant Kuiper Belt, turns out to have been incomplete. What was hidden is not simply new data points, but an entire mechanism of atmospheric chemistry and environmental interaction that no previous instrument could detect. JWST has shown that on Pluto, the haze enveloping the dwarf planet actually acts as a solar-powered cooling system, a process unseen in any other world. Before we start, smash the like and subscribe buttons for more updates. The key is the layered bluish haze that pervades Pluto's thin atmosphere. When the New Horizons mission brought back images of Pluto's atmospheric haze and multi-layered structure, scientists were struck by its intrigue but lacked the spectral tools to unpick the chemistry. JWS changed that. It revealed that the haze is composed of organic molecules born from solar ultraviolet radiation interacting with methane and nitrogen in Pluto's atmosphere. Those organic hazes then absorb sunlight and re-radiate energy in the infrared, essentially cooling the atmosphere from within. In other words, the haze is not just a passive blanket of particles, it is an active, dynamic climate component. JWST's ability to isolate thermal signals of both Pluto and its moon Charon, differentiating between the two and measuring the spectral signatures, made this discovery possible. The result is the confirmation of a long-held hypothesis: Pluto's haze-driven cooling mechanism. This hidden mechanism matters enormously. It means Pluto is not simply warming or inert, it's engaged in a subtle interplay between solar irradiation, atmospheric chemistry, and surface-atmosphere coupling. That makes Pluto far more Earth-like, in the sense that it hosts an atmosphere with active processes than most had anticipated. The discovery forces scientists to revisit models of how dwarf planets evolve, how atmospheres can persist in cold outer solar system environments, and how hazes and organics might regulate temperature far from the sun. The fact that such a process exists on Pluto opens the tantalizing possibility that other small icy worlds, for instance Triton, a moon of Neptune, or Titan of Saturn, may host analogous atmospheric systems that we have simply missed until now. To appreciate the full weight of the finding, one must understand Pluto's context. It orbits in the Kuiper Belt, a region of icy objects beyond Neptune, and its atmosphere is extremely tenuous compared to Earth's. Prior observations from New Horizons and ground-based telescopes had established that Pluto has surface ices of nitrogen, methane, and carbon monoxide, and that its atmosphere contains nitrogen and methane in equilibrium with those ices. But the dynamics of how its atmosphere is cooled, how hazes form, and how energy is exchanged were largely speculative. JWST filled that gap. What used to be an outline of a world has now become a detailed blueprint of interaction. JWST observed that when sunlight strikes Pluto, methane and nitrogen in the upper atmosphere react under ultraviolet light and with cosmic ray inputs to produce complex hydrocarbons and organics. These particles aggregate, become the multi-layer haze, and absorb incident sunlight. Instead of simply letting that sunlight warm the atmosphere or the surface, the haze transforms the energy and re-radiates it in the infrared, effectively siphoning heat away. The cooling effect is not trivial. It changes how energy flows through Pluto's atmosphere, how surface ices sublimate, how the atmospheric pressure might vary over time, and ultimately how Pluto's climate behaves across long seasons. To find such a system on a distant dwarf planet is remarkable. It was effectively hidden because earlier spacecraft lacked the infrared sensitivity and spectral resolution to detect the process. The implications ripple outward. One strong implication is for the origin and evolution of atmospheres in the outer solar system. If Pluto's haze mechanism enables the retention of a tenuous atmosphere in a region where solar input is weak, then models of atmospheric escape, volatility loss, and longevity must be revised. Traditional thinking held that small icy worlds far from the sun would lose volatile components quickly, or host only passive static atmospheres with little active chemistry. Instead, we now see that Pluto has an active chemical climate engine. That suggests that other Kuiper Belt objects, many of which we cannot yet observe in detail, may have similarly rich and dynamic environments. It widens our horizon. The outer solar system is not just a frozen waste, but potentially a theater of subtle but significant processes. Another implication is in comparative planetology and how we understand Earth's atmosphere in a broader context. The organic hazes above Pluto, created by solar irradiation of methane and nitrogen, may offer analogs for early Earth atmospheres, when Earth itself had far more methane and nitrogen, and haze layers may have played a role in surface cooling or UV shielding. In that sense, studying Pluto gives a natural laboratory for ancient atmospheric states. The fact that Pluto's haze is acting to cool the atmosphere rather than warm it challenges assumptions about how organics interact with radiation across a variety of bodies. It means that climate feedbacks on small bodies can behave in ways that differ substantially from our terrestrial expectation. From an exploration and mission planning perspective, the discovery reshapes priorities. If Pluto is more dynamic and complex than assumed, then any future missions to the outer solar system might prioritize revisiting Pluto or targeting similar dwarf planets and Kuiper Belt objects to capture active atmospheric chemistry. The value of high-sensitivity, broad-wavelength infrared observations is underscored. JWST's ability to peer at wavelengths longer than previously accessible allowed the detection of those thermal signatures and revealed the cooling process. It sets the stage for the next generation of telescopes and missions to focus on remote, faint worlds not as static relics, but as evolving, interacting systems. Moreover, the discovery of a climate-type mechanism on Pluto changes our classification of dwarf planets and small bodies. Rather than being passive monoliths of ice and rock, these bodies may host layered atmospheres, surface atmosphere feedback loops, seasonal ice cycling, and organic particle-driven processes. That elevates them in our understanding from footnotes to full participants in the story of the solar system's evolution. Pluto, once considered an outlier and demoted at least in popular conception from full planetary status, is now reveling in a resurgence of importance. It commands renewed interest, not just as a distant curiosity, but as a world on which chemistry and climate meet at the edge of the sun's domain. On the observational side, the discovery provides a benchmark for refining our models of haze formation. We now know that organic molecules generated via methane and nitrogen photochemistry can accumulate to the degree that they exert macroclimatic influence. That opens questions about the exact rates of production of these organics, the vertical structure of haze layers, how they interact with surface ices, and how they evolve over time as Pluto's distance from the Sun changes across its elongated orbit. The warp of seasons on Pluto, the sublimation of volatile ices from surface to atmosphere and back, the layering of hazes and their thermal impact, the whole package must be reconsidered. Pluto becomes a case study in how cold, distant worlds can nonetheless host sophisticated feedbacks. In addition, scientists must now reconcile how Pluto's haze-driven cooling mechanism coexists with what we know about surface geology and ice dynamics. The New Horizons images showed Pluto's strange terrains: nitrogen ice glaciers, water ice mountains, methane glaciation, pits, dunes, and flows. Now we see above that surface an active atmospheric process that may influence how those ices move, how the atmosphere responds to solar heating, and how volatile exchange occurs. The interplay between atmospheric cooling and surface ice behavior may govern, for example, how quickly nitrogen ice sublimates into gas, how gases freeze out again, how surface pressure varies, and how ice flows might be driven or suppressed by atmospheric coupling. The discovery thus requires integrated models of surface, atmosphere, and radiation for Pluto. One cannot fail to note the narrative of hiding that frames this discovery. For years, Pluto lingered in the periphery of human curiosity, a cameo in the New Horizons flyby, then years of relative silence. The hint of complexity existed, but our tools lacked the sensitivity. JWST's unveiling of the haze cooling mechanism is akin to opening a door we didn't know was locked. It underscores how technology and instrumentation shape our view of the universe. What we considered known can shift radically when we lift the veil. Pluto is now front and center again. Equally compelling is how this shifts our understanding of atmosphere retention. For an object like Pluto, far from the warmth of the Sun, the standard model would predict a thin, gradually escaping atmosphere with few active components. Instead, we see a resilient atmosphere shaped by organics and haze, actively radiating energy. That implies that even in the cold reaches, bodies may maintain atmospheres longer or in different ways than previously thought. It challenges the line between active planetary body and passive small icy rock. Pluto becomes a boundary case, straddling the worlds of planets and minor bodies, and now with a far richer biography. Looking ahead, the broader implication extends to exoplanets and remote objects. If haze-driven climate mechanisms can operate on a small body like Pluto, then when we observe exoplanets or distant dwarf planets, we may need to incorporate similar processes. The discovery invites scientists to refine atmospheric models to include haze cooling, organic particle interactions, and radiation coupling, not only for large planets but for smaller icy worlds. It means that the diversity of climate regimes in the universe may be far greater than our Earth-centric models suggest. If you liked this video, please give it a like and subscribe to our channel. Also, leave your comments below and tell us, what are your thoughts on what James Webb just found on Pluto? We want to hear from you. Thank you for watching and see you next time.